Alright, folks. Today we'll talk about what I consider the most important result in dynamical system, certainly in a planar system, and this is the well-known Poincare-Bendixson theorem. Poincare-Bendixson theorem essentially gives us a complete picture, a complete picture of the phase portrait in a planar system. So we begin with the so-called Bendixson alternatives. So let's consider the following general planar system. Let's say x and y is in some domain in R2. So I need all the partial derivatives. I need all the partial derivatives to be continuous in omega. And we further assume that the system has finite many equilibrium points. And let's let S denote the limit set, and that can be either the alpha limit set or omega limit set. Is the limit set for a solution. Bendixson alternative claims that S has to be the following. Has to be one of the following. Okay. So giving you a solution curve on the xy plane, where do you think this limit will be? What do you think the limit set will be? Bendixson alternative says this set S is either an equilibrium point. Okay, this is something we're familiar with. Or a closed solution curve. And this is what we refer to as the limit cycles or closed orbit that we mentioned about in the previous two sections. And the third possibility is it approaches not a closed solution curve, but what we call a cyclic graph. That has equilibrium points being the vertices, okay, with vertices that are equilibrium points and edges that are solutions, okay, that are solution curves. So this gives you a complete picture of the limit set. The first case here, this is a solution curve. It can approach a equilibrium point. A solution curve can also approach, well, a limit cycle, So this is a closed solution curve. The limit set of this can be this whole orbit, okay, this whole orbit. The third case is it could be a cyclic graph with vertices being equilibrium. Let's say here we have 1 equilibrium, 2, 3, and 4. And there may be solution curves connect them all. Okay? So here this one has like 4 equilibrium points with solutions connect them all. Then the limit set of a solution curve could be this what we call cyclic graph. Could be this edge along this part. Okay, could be this. And notice this is different from a closed solution, because this is not a closed solution. This is a closed solution. These are equilibrium points with different solutions along the edge. Okay, so the limit set for this solution curve will be this what we call cyclic graph. Okay, and that is the Poincare-Bendixson. This is the Bendixson alternatives. And here is the Poincare-Bendixson theorem that this section about. So the Bendixson alternative says, the limit set of any solution curves is either a closed orbit or equilibrium or a cyclic graph. Here's Poincare-Bendixson theorem. So we'll consider a region that's closed and also bounded. Closed and bounded, that's pretty easy to understand. And here's something else that we talked about before. I need this guy to be positively invariant. Think about the meaning of that. That means all the solutions will be trapped inside, okay? So we can also call this a trapping region. In other words, there won't be any solution curve leaving this region. Poincare-Bendixson theorem says, well, if this region R trapped all the solution curve but does not have any equilibrium points, contains no equilibrium points, what do you think is going to happen to the solution curve? The solution curves are not leaving the region. It cannot approach any equilibrium points either, because there is no equilibrium points. The Bendixson alternative says there is only one possible limit point. That is, there has to be a closed solution curve, being its limit cycle. Because there is no equilibrium, there is no cyclic graph. It has to be a closed solution curve, and that's what Poincare-Bendixson theorem says. If it has no equilibrium points, then R contains a closed orbit or limit cycle, okay? That indicates the existence of a periodic solution. In other words, both X and Y are both periodic. Alright, so this theorem shows how do you prove that a system actually has a limit cycle, actually has a periodic solution, by construct a positively invariant region and that has no equilibrium points in there. So that's Poincare-Bendixson theorem. So graphically, I'll show you an additional example, but graphically, if you have a region that's R, everything will be trapped inside. It's not going to go outside anywhere. So any trajectory has to go somewhere, but there's no equilibrium inside. So that indicates there got to be some closed orbit that's hidden inside that you don't see it right away. But that'll be the limit set for this solution curve. Okay, so that's the limit cycle that's hidden inside this region. So now we'll show you an example on how do we apply this Poincare-Bendixson theorem. Let's show this van der Pol system has a closed orbit. How do I show this one actually has a closed orbit? Well, according to Poincare-Bendixson theorem, you need to somehow come up with a closed and bounded region that's trapping, okay, that's positive invariant, that also has no equilibrium. Let's think about the equilibrium point for this. All right, you can easily tell the only equilibrium for this guy is 0, 0. So the region R should not contain this point. Somehow you need to get rid of this point. And creating a positive invariant region is not exactly easy, and that's often the key in research. Okay, that's often the key in research. So here I will briefly describe this region for this system that I talked about. See 0 here, I do not want it to contain this guy, so I will remove it. So I'm going to make a little circle around the origin, make the radius 1, and then I pick some edges here. Call this 4, -4, +4. And there's no standard procedure coming up with this, okay? This one somehow just works, all right? Oh, sorry, that's not the way to go. You see this region? I'm claiming this region that's closed and bounded, but not including the origin is the positive invariant set. So in other words, I want to show along those edges there is no trajectory coming inside. So that obviously requires us to do some detailed calculations here. All right, so I'll try my best to explain why this set is positively invariant. Once I can show this guy is indeed positively invariant and there is no solution curve leaving this region, then according to Poincare-Bendixson theorem, this has to have a hidden limit cycle somewhere inside. So let me show you that on x equal to 4, so along this edge, okay, this is the part that I'm trying to do first, along this edge. So I have to go through all the edges, including the side, the circle inside. Along this one, I want to show everything is pointing out, pointing inward, okay? It's not come out. So I'm going to calculate dx dt. So I look at x prime. I want to show this is negative. So this is the equation for x. But x is 4. Y is something between -4 and 0. X is 4. So that turns out to be x prime. Well, obviously, if y is a number between -4 and 0, is it pretty trivial that this is indeed always negative? Dx dt is negative, indicating x will be decreasing, so the trajectory is always pointing to the left side, okay, moving inside. Next, I'm going to show you along this edge, okay, along this edge. The equation for that edge is x plus y equal to 4. All right. So this is at any point on this edge, x plus y is always 4. Outside, it's going to be bigger than 4. Inside, it'll be less than 4. So one way that I can do this is I'm going to calculate x plus y prime. If the sum is negative, meaning it has to pointing moving inside instead of outside, because on the outside the sum of x and y is always bigger than 4. So I do x plus y prime, do x minus y minus x cubed, and also plus x. Add up those two terms. But because we're talking about on this edge, so y is always 4 minus x. Y is 4 minus x. And this is something you can show that I will not do the detailed algebra here, but whenever x is a number between 0 and 4, you can show this is indeed negative. Okay, you can try to prove this yourself. So we say x plus y, the sum is always decreasing, and the vector field point into R, okay, into this region that you created. So there are obviously a few other edges that unfortunately we have to show carefully, and you can try to do this as a practice problem. So here we say similarly x plus y equals negative 4, which refers to this edge. We can show x plus y prime is positive, and on this edge y equal to negative 4, y equal to negative 4 is this guy right here, and x is between 0 and 4. You're going to calculate y prime. Y prime, okay, y prime is x, okay, y prime is x. Y prime is x, but x is positive. So on the bottom edge here, that's where y equal to negative 4. On the bottom edge here, y prime is positive, so the vector field will pointing upward, in other words inside. So finally, I like to show that along this unit circle here, the trajectory will also pointing inside. And how are we going to show this? Here's how. We're going to convert this into polar coordinates. I want to show r prime is greater or equal to 0 on r equal to 1. When r is 1, okay, when r is 1, I want to show r prime is positive. In other words, the distance to the origin will increase, so it'll pointing outward. And this is a standard equation that r prime, so you can just verify this by yourself, okay, when you try to do polar coordinates. It's always x prime plus y prime. And I plug in x prime, and then plug in y prime. And notice those two terms are cancelled. Those two terms are cancelled. And the answer turns out to be x squared times by 2 minus x squared. So sure, there's still some x term in there, but I can easily tell this is always positive. So it's this guy, all right, because x is between negative and 1. So this is strictly what? Positive. So that's why r prime is actually strictly positive when r equal to 1, okay, when r equal to 1. At every point on the boundary of R, the solution curves are moving into R. So nothing is leaving R, and R is invariant. Furthermore, the region that we created contains no equilibrium. By Poincare-Bendixson theorem, there exists a closed orbit. Okay, so you can actually take this system, plug it into online plotter, actually plot the graphs. I'm pretty sure you'll find out there is indeed a limit cycle. Okay, I will leave this to you. All right, so that is a quick example on how do we apply Poincare-Bendixson theorem. And that's the end of all the techniques of planar system. Okay, nonlinear planar system. What's coming up next will be a lot of different examples on how do we apply all those techniques that we learned to different systems. All right, and then the final topic will be bifurcation theorem that some of you might be wondering about. So what's coming up next, once again, are examples and bifurcation theorem.